Assalamu alaikum. Today we are going to solve solution of Volterra integral equation of first kind by solving this example. Before solving this example, we will recall the concept of Volterra integral equation, which is h of x into u of x is equals to f of x plus lambda integral from 0 to x k of xt u of t dt. Now it's first and second kind. In first kind, h of x is equal to 0. So this, when there is an unknown function h of x is equals to 0 is equals to f of x plus lambda 0 to x k of xt u of t dt. So now on the left hand side we have no unknown function, and for the second kind h of x is equals to 1. So this gives u of x is equals to f of x plus lambda 0 integral from 0 to x k of xt u of t dt. Now come to the example. We have f of x is equals to limit from 0 to x e of xt y of t dt. F of 0 is equals to 0. This f of 0 is equals to 0 tells us whether the given equation is continuous or not. So for this we will put x is equals to 0 to check the function is continuous. Here the kernel here is the kernel e of x minus t and its partial derivative partial by partial x e of x minus t are continuous. Now differentiating both sides of equation 1 with respect to x. So this is of equation 1. F prime of x is equals to integral from 0 to x partial by partial x of the function of xt y of t dt plus e of x minus x. So now we put the upper limit in t, okay, x minus x y of x dx by dx minus, here comes minus x minus 0 lower limit y of 0 d0 by dx. F prime of x is equals to 0 to x e of x minus t, derivative of x is 1 y of t dt plus x minus x0 e power 0 y of x into 1 minus 0. This gives you 0. F prime of x is equals to integral from 0 to f x e x minus t y of t dt plus y of x. So by rearranging this equation, y of x is equals to f prime of x minus 0 to x e x minus t y of t dt. Okay, now we compare this with the general equation of Volterra integral equation of second kind, which is this one. Here y of x or u of x, f of x is equals to f prime of x, lambda, this lambda is equals to minus 1, kernel k of xt e into x minus t. Now we find kmxt be the mth iterated kernel. We have to find these mth iterated kernels. As we know, k1 of xt, k1 of xt is equals to k of xt, kmxt is equals to integral limit from t to x by splitting this integral t of x k from x to z k minus 1 z to t by introducing a new variable, this one z. Integrate this with respect to z, where m is equals to 1 2 up to so on. By equation 4 we have k1 of xt is equals to k of xt, which is e x minus t. This is the kernel, and kernel k of xt, k1 of xt is equals to this one. By putting m is equals to 2 in equation 6, this is the equation 6, k2 of xt limit from t to x k of xz k into 2 minus 1 z of t dz, limit from t to x e x minus z, where this comes k of x z is equals to x minus z, e into z minus t dz, e into x minus t, this gives you e into x minus z plus z minus t comes x minus t. So x minus t, because there is no element of z, so we taken out this x minus t limit from t to x dz, x minus t z limit from t to x e into x minus t x minus t. Again, by putting m is equals to 3 and 6, k3 of xt limit from t to x k of xz k to z t dz, Again, integral from t to x, e into x minus z, k2 of zt, this one. By putting this, we put z instead of x, dz. Now taken out e into x minus t, integral from t to x, z minus t, dz. Okay, now we have e into x minus t, z minus t, 2 factorial power. By solving the integral limit from t to x, we get this. Again, by putting m is equals to 4 and 6, k4 of xt, integral from t to x, k of xz, k3 of zt, dz. By putting value of this and this, we got this equation. By solving again this equation by previous method, we got e raised to power x minus t, z minus t, q3 factorial. So it's mathematical induction. We have km of xt, e raised to power x minus t. Here you can see that whenever we have k2, this one m minus 1 power, when we have k2 of xt, this gives you 1 less power, 1 m minus 1. So from this we have e into x minus t, z minus t, m minus 1 factorial. Now we'll find the resolved kernel of equation 3. Our xt lambda is equals to summation m is equals to 1 to infinity lambda m minus 1 k m of xt. You have to remember this is the general form of resolvent kernel. Summation m is equals to 1 to infinity lambda is equals to minus 1. We has already find this. Lambda is equals to minus 1 km of xt. Summation m is equals to 1 to infinity, putting this minus 1 m minus 1 km xt. We can write it as km xt. Here we have minus 1. We have switching these signs, plus minus and so on. By putting values of k1, we have x minus t, k2 e raised to power x minus t into x minus t plus e raised to power x minus t into x minus t square divided by 2 factorial minus e raised to power x minus t cube divided by 3 factorial and up to so on. And then by taking out this e raised to power x minus t, we have 1 minus x minus t 1 factorial plus x minus t 2 square divided by 2 factorial power 2 factorial minus x minus cube 3 factorial up to so on. X minus t, this makes a series e minus x minus t. By solving this, e raised to power x minus t minus x plus t e raised to power 0 is equals to 1. So hence the required solution is y of x is equals to f of x plus lambda limit from 0 to x r x t lambda f of t dt. By putting values of these, we have y of x is equals to f of x is equals to f prime of x minus lambda is equals to minus 1. So this gives you minus limit from 0 to x r of xt. Resolvent kernel is this 1 f prime of x, so f prime of t dt. By solving this, integral derivative cancel. Y of x is equals to f prime of x minus f of t limit from 0 to x. Y of x is equals to f prime of x minus f of x. So this is the required solution.